Welcome to the Crazy Wisdom Podcast. My guest today is Sergiy. He is the CEO at Quilter, and we've already had one phone call to talk about exactly what Quilter is and what they're doing. And we talked about chips and what did we talk? Neuromorphic chips and other things. That's not what you're working on, but excited to talk about what you guys are working on. Welcome to the show.
All right, thanks for having me, Stuart. I'm excited to be here.
I just love, so let me set this up a little bit more. AI is changing a lot of things. It's very hyped in some ways, and a lot of that hype is going to turn out to be BS. And then it's also not hyped in other ways, and people are completely undervaluating it. But I think one thing that is somewhat certain to say is that most investors are now moving outside of software, not most. I think the intelligent investors are moving outside of software into deep tech and hard tech, because it feels like the business angles of creating software, like static software, are probably going to change significantly. And so you're doing something that is the intersection of both of those things, the deep tech and the AI. What exactly are you doing?
Yeah, so what we do at Quilter is we are working on automating a large portion of the process of designing a circuit board. So as you might know, circuit board design is a slow and laborious process for something complicated like a computer motherboard. Easily takes many months to do. And we think that there are parts of that take up as much as half of that time in total that we can completely automate in the long term.
And now, is this automation, is it completely software based? Well, is designing hardware, well, okay, here's a better question. What aspects of designing hardware are software based?
Yeah, it's a great question. So in our case, maybe helps to give a little bit of background so that listeners can picture a little bit of what we're talking about. So for anybody watching, this is the kind of thing we're talking about. I'm just holding a computer motherboard in my hand. This is not something we designed, but this is the kind of thing that we aspire to design. The basic process for designing a circuit board like this, I think of in kind of three major steps. The first is to draw basically a block diagram that says what chips am I going to use, what connectors am I going to use, and how do I string them together to perform some function. This is typically called a circuit schematic. And you can picture it as a block diagram or a flow chart, but with a lot of detail. The second part of designing a circuit board is to actually make a physical blueprint that a factory can then create. So that's where you're actually specifying, here's the size of my board, connector on the left, chip in the middle, other connector on the right. And the kind of hard part of it is that you are physically drawing all of the copper and all the fiberglass that will kind of exist and glue together all of those chips. Finally, of course, you take that blueprint. This is called a PCB layout for the listener. And then you send it to a factory who then puts it together, creates it, get the board on your desk, usually find out you screwed something up and you go again. So what we are trying to do is automate completely that second step called layout. And so to answer your question most directly, we believe that software can achieve this in full. So software is kind of going to ingest the schematic, the logical description of what the board will be, and arrange kind of where all the components go and how all the copper glues them together in a way that is manufacturable, in a way that the physics is going to actually work, in the way that the board doesn't catch fire, doesn't fail FCC emission criteria, and all that good stuff.
Okay, this is so interesting because you've got we were talking about software, we got hardware. I love talking to hardware founders because it seems really difficult, and they do it, and they all seem kind of crazy because they're doing it. Not to mention that, not to say that software is easy, but it definitely feels easier. And you actually have experience in helping to build actual hardware, and not just any hardware, rockets going into space. And so if AI is able to change the software game significantly, what are the things beyond the software that people are going to have to start concentrating on in order to get that next job? Because that's the thing that everybody's worried about with AI is like, well, what am I going to do now? And I don't think doing things is going away. I think it's going to be really hard to do a lot of things still. It's just going to be doing things in space. It's okay if you don't have like a specific answer to this specific question, but what's your thoughts on this? Like, of what are the things that are going to be really hard still to do?
Yeah, what are the things that are going to be hard to do still? I mean, I think that the probably one of the hardest things to do in general in engineering and in starting a company, whatever else, is like actually having a good insight into what should be built, actually having empathy for a customer, right? Like we spend like I think that especially as we grow, like when for a child they look at something obvious, and you know that's obvious to us, and they'll say like, oh wait, why is this the way that we do this, right? I think I heard a talk where somebody said like, why do we have a barcode sticker on each individual apple? Like, why does that make sense? Why do I have to peel that off every single time? Right. But like as an adult, like you're used to that. You go to the grocery store, there's a sticker on the apple, you scan it, and then you wash it off and you deal with the glue, and it's annoying, but like you don't question it. And so I think that like one of the hardest things for an engineer or for a CEO or for, I mean, almost anybody is to like keep that child mindset and notice these things that are ridiculous, that shouldn't exist, but we've gotten completely used to. And I don't foresee like AI tackling that soon. And so I think that's where so much of the value will be. And I don't think it's of like creating a new company, a new product. I think it can be like, I'm an individual engineer at a company. I have to do a process. I have to ship my product, but the way I'm asked to do it is ridiculous. So I go and I convince, you know, my management, my peers that like, there's a different way we should approach this that benefits the whole company. That can happen on an individual scale, not just on a company product CEO scale.
Yeah, because that's still the business. That's still the business is improving things, solving problems and such. And like all those
Right.
things are going to go away. I loved what you said about uh the insight. It's like insight and taste, and sort of desire or wants. Because I had a great conversation with Stephen Wolfram last week. I had interviewed him in 2018, and back in 2018, he said, you know, once the computers get really, really good at what doing what we want, we're still left with the problem of what do we actually want. And that brings in this sort of like subjective nature, because correct me if I'm wrong, that insight into a problem feels like it's very subjective in nature. Like it's only something that a human could, you know, AI might be able to simulate that one day. Currently doesn't simulate that. Is that accurate? Anything you would add? Anything you agree or disagree?
Yeah, I mean, certainly for the human side, like that is probably the key line of thinking that separates like really great contributors in a society from, you know, people are just kind of doing what they're told and proceeding with the marching orders. I'm not aware of anybody even tackling this question in AI in any kind of serious productized sense. I mean, I have no idea what that would even look like at this point. I mean, I'm sure we'll be surprised in a couple decades or maybe sooner. I don't know, but today, like I don't see, like I see people doing roughly what we're doing, which is like, here is a task that can be automated. That like when a human says, "Please do this," right now another human says, "Please do this." I will do it, but like software could. And then now we have both of those humans thinking about the creative side, which to me is a benefit. I mean, the
Mm,
other thing is like to put a number on this, right? Like in my industry in particular, so in electronics and PCB design, we have an enormous, a tremendous scarcity of electrical engineers, right? Like the CHIPS Act alone, you know, is slated to create, I don't want to cite off the top of my head, but some like tremendous amount of jobs that'll take us 20 years to fill, and we're going to fill it in presumably 4 years somehow, right? So like there's so much work to do. Let's free up the time that's being spent on tasks that can be automated, because we need those brains on the other tasks that can't be.
great. Okay, so let's go into that electrical engineer issue. I basically know nothing about electrical engineering. What I love about doing this podcast is I get to talk to people like you who know a lot about it. And like once I do one of these episodes, I can then go further and further into it. But it usually takes me talking to another human being to get interested enough into it. What are the fundamental things that, like what's the beginner curriculum for electrical engineers? What are the, is it a lot of math? Is it a lot of physics? What does somebody need to know in order to become an electrical engineer?
Mm-hmm. Yeah, so let me answer this question in two different ways. One perhaps from the ultra fundamental and one from the practical angle. So like from the very ultra fundamental angle, what an electrical engineer does in any context, right? And I'm picturing somebody working on circuit boards, working on chips, or working on power stations, right? They are kind of masters of the Maxwell equations, right? Like we have this fundamental set of laws that govern electromagnetic fields, and we can manipulate those electromagnetic fields in different ways to accomplish work, right? Whether it's to compute something or to deliver power or to move something or whatever else might be. Now, ironically, a lot of electrical engineers, you know, fear Maxwell equations and fear that level of detail, and a lot of the core course curriculum doesn't actually dive in horribly deep into them unless you're kind of specializing in RF and microwave and whatever else, and you like physics. What a typical electrical engineer will start with is just basic, what's kind of called circuit analysis. So we have these fundamental Lego blocks that manipulate electromagnetic fields in certain ways. And these fundamental blocks are things like a capacitor, a resistor, a transistor, a diode, basically different ways of manipulating electromagnetic fields, right? Just channeling power in a certain direction, storing power, reserving it for a later time. And then you can turn that into kind of two fundamental directions in my mind. One is compute, right? So you model a 1 or a 0 as there is charge or there is not charge, and then you move charge around, and then that gives you ability to add, subtract, and then eventually to build an operating system and have a Zoom call. The other is kind of power, right? So like I have an electric car, I need to turn the wheel. How do I take a bunch of stored charge and turn it into work, turn it into motion? And then that's like a different way of kind of managing electromagnetic fields. Maybe a third one would be communications, right? So I have an antenna, I want to communicate with another antenna, like think FM radio, or think satellite phone, or think your phone talking to a LTE tower, right? You're again kind of manipulating charge to create an electromagnetic field that goes from one device to another and then carries information, carries ones and zeros that can then communicate. Yeah, let me know if I answered your question. Maybe I kind of went off on a tangent,
And
but I can
no,
dive
you
in.
did. You did, and there's a lot more follow-up questions. What is an electromagnetic field, and why was this the thing that we needed in order to make computers?
Yeah, good questions both. So what is an electromagnetic field? I don't know if I can really give a really great answer to it. It is at the very least a model of the world that tends to explain behaviors that we see when we play with charges and we play with magnets, but primarily with charges, right? So if you take a balloon and you rub your head on it, right? Eventually, if you hold the balloon next to your hair kind of stands up and attracts to it. So like explaining that phenomena is done by by the Maxwell equations and the
Mm,
electric field there. And then magnetism kind of comes from relativity, actually. So when you start thinking about purely electricity and you start thinking about reference frames, what reference frame you're in, what you observe if you're in one reference frame versus the other, one of the things that falls out of that, it looks like magnetism. So in some sense, like electric fields plus relativity equals what we think of classically as electromagnetics. Now, why do we need it for compute? Strictly speaking, we don't. There are like historical designs of like mechanical computers that existed long before people really learned how to manipulate electromagnetic fields. And so in principle you could make a mechanical computer just fine. Problem is mechanisms in our world move really slowly, they break, they're brittle, all that stuff. Whereas with electromagnetics, well, in the electrical domain, you can make transistors, chips that can operate at gigahertz, or really exciting, like the promising stuff that might happen in another decade or two or something, I don't know, is moving to higher frequencies of the electromagnetic spectrum, specifically photonics. So there might be not like radio wave chips where we're talking about gigahertz and antennas, but like light wave chips where we're talking about ridiculously fast frequencies and light-based kind of gates and logical operations. But this is like, research level work today. But roughly speaking, that's all speed, right? Mechanical computer is going to operate at like, I don't know, a couple of hertz. Computers with electricity can operate at gigahertz. Hopefully, light-based computers will operate at terahertz, and faster is better.
That's super interesting. Now I get it. Now I understand why electrical engineering was so important for creating the semiconductor. There's one more question I have, which is I've been reading the biography of William Shockley, who is the founder of, I believe it was Fairchild Semiconductors, and he, I believe, invented the semiconductor chip. And I was reading in this book, it mentions Einstein relativity, Einstein calling the spooky action at a distance of quantum mechanics the spooky action at a distance, which is a great name. And then seeing that, and then somehow William Shockley, then this is the part I missed. I couldn't understand what it was talking because it got very technical. Something related to quantum mechanics allowed for the semiconductor to exist. Is that right? Do you know anything about that? The relationship between quantum mechanics and semiconductors?
Sure, a little bit. Like I'm not a semiconductor designer. I don't create chips or PN junctions, so I'm very likely to butcher this. But I can
You
give a
should.
few brief ideas. Yeah. So when Einstein was talking about spooky action at a distance, he was talking about quantum entanglement,
Yep.
which to my knowledge does not currently play a role
Okay.
in at least traditional semiconductors. It's a kind of an entirely different phenomena. But things that are relevant in conductors are these things called energy bands, and this kind of concept of tunneling. And basically, these are phenomena that we observe that are explained by the Schrodinger's equation, but that are very difficult to intuit from the way that we picture the world because quantum mechanics doesn't really show up at our scale. So, like I'll give an example of tunneling in particular. Tunneling is this concept that like the kind of layman's example is that like you have a ball, it suddenly shows up on the other side of a wall.
Oh,
But like it didn't have the enough energy to go over that wall. So how did it do that? And if you kind of follow the Schrodinger's equation, you really kind of see that it doesn't really have a position. It has a wave function of positions, and there's probabilities associated with that. And it's a probabilistic phenomena. And even though it doesn't have enough energy to go over the wall, there's some probability still that it ends up on the other side. And we actually observe that and it happens. But like basically speaking, yes, like quantum mechanics certainly plays a role, especially in modern semiconductor design, especially now that we're getting to these really small nodes, and these effects like tunneling and even like the principle of band gap was important a long time ago, are something that these engineers have to deal with. But I'm no expert. Like you should talk to a chip designer to really see like where that really comes in and at
oh,
what
interesting.
level. And
Okay, because you guys are doing the circuit board itself, and you're connecting chips together on a circuit board.
yes,
Okay.
precisely.
And why is copper such an important part of this?
Yeah, good question. So to put in perspective, right, we were just talking about things that are on the scale of nanometers, right? Like we're talking about chips and whatever else. Circuit boards are more on the scale of like millimeters and greater, right? So a circuit board, the one I held in my hand, is I don't know, maybe 20 centimeters by 30 centimeters, something like that. But like the smallest feature on it is going to be like a little piece of copper that's a fractions of a millimeter in size. So much, much, much bigger than quantum. We certainly don't have to deal with quantum,
Uh,
which I really appreciate
oh,
given the
interesting.
difficulty of that. Nowhere near it. We only have to deal with kind of classical electromagnetics and thermodynamics. But to answer your question, why copper? When you connect chips, you want a efficient connection that doesn't waste power, and that doesn't basically, yeah, that just doesn't waste power and makes you take less power to communicate from one chip to the next. The best conductor, at least that I'm aware off the top of my head, is gold. Gold's expensive. Let's not do that.
Uh,
Silver is pretty darn good. Very expensive. Let's not do that. Copper is the next best. Relatively cheap. And so hence we are
Interesting.
using copper.
That's okay. That's interesting. Uh, so okay, we got copper. We've got the conductors themselves. You talked about the light things, but that's kind of like still science fiction. We've got AI who's going to design. Well, actually, yeah, let's go into AI. One of the most interesting conversations I've had in the last few months is with a guy building robots. And he and none of his colleagues use ChatGPT for any part of that purpose because it just doesn't know, it doesn't have enough expert knowledge, I guess, about robotics or about the physical world. Can you talk more about the challenges in terms of the physical world that are really hard to use AI for? Yeah, let's start there.
Sure. So let's separate a little bit, like ChatGPT and AI as a whole. I think that's a useful delineation. I think ChatGPT is specifically a large language model, right? Which means that it is intended to take in sequences of characters, right? Like basically sentences, and to predict the next word, the next set of words, the next set of sentences that would follow that. And then you can basically use that kind of system to trick it into telling you stuff, right? Like, so you might say, teach me what a capacitor is, and then it has read somewhere on a forum that somebody asked that question and somebody responded with an answer, and then it can take like kind of the interpolation or the average of millions of those answers across the internet and like summarize them for you in a legible way. And it's magic, right? It's incredible that this is possible and that it stores the world's information like this, and that's great. Now, but that's one very specific type of neural network that's doing one very specific task, right? In general, when you think about AI as a whole, you're thinking about all kinds of different tasks, right? So like as a big contrast, take Tesla's autopilot, right? Like here, you are taking raw pixels coming in from cameras, and you're eventually converting it into actuator outputs, right? Like how much throttle to apply, how much steering to apply. Your input is not a sequence of tokens in language. Your input is really images. And then your output isn't a sentence, it's control outputs, right? And so there's many, many, many such systems that one can build with different advantages and drawbacks. Now, the nice thing about LLMs is they are becoming a commodity, right? There are, I don't know how many dozens of them by now. Some are commercial, some are free, have different advantages and context lengths. Awesome. So if you have a task that requires you to speak in natural language, especially about something that's frequently written about on the internet, like solved problem. I mean, okay, maybe that's overstating it, but like you probably shouldn't go and train one yourself because it's very hard to duplicate the state of the art.
Yeah.
But like if you have some of these other tasks, like I want a robot to balance itself on its two legs, like not solve problem. You can't just go query ChatGPT and have it work or download an equivalent. Now you have to design that neural network. You have to train it, and that's difficult. And so that might be where.
Are computer vision algorithms becoming a commodity at all, like in the same way, or is it still very much behind closed doors?
Yeah, that's a very interesting question. I struggle to answer that in generality, right? Like I think at the kind of front end of computer vision is the question of how do we ingest the information that is an image? So basically a 2D set of pixels with all their RGB colors or whatever. And then in the middle is kind of like how do we process, how do we build a function that can make some prediction? And at the output is like what kind of control do we want from it? So there's still plenty of interesting discussion happening at the front side of like how to ingest an image, right? Like the king neural network for this was, from historically a convolutional neural net, which Jan LeCun developed in I think the 90s and got really sped up by GPUs in 2012, 2013 when AlexNet happened and like the initial boom of neural networks happened. But like since then, people have applied transformers, which is this architecture that made its name in the large language models, also to images. And so now, like as a computer vision engineer, you might have a choice of like, do I choose a convolution or do I choose a transformer for my task? And you might go and try both and just see whatever works better. That part, there's something to stand on. And at least for us at Quilter and in my experience, the harder part is like, then how do you create the correct kind of output and actually find the weights of the neural network that do something useful, and that requires good architecture, good engineering, lots of scale, lots of like non-obvious questions to be answered about the architecture that you're setting up.
Okay, that's super
So
interesting. Yeah. Interesting. This is all these new things. I'm gonna go back and LeCun developing a commercial network or no, a commercial neural network in the 90s. AlexNet. Oh, go for it.
Yeah. So Jan LeCun developed a convolutional neural network.
Yeah.
Convolution is a type of mathematical operation where you can basically imagine an image as a big grid, and you take a small tile and you move it across that grid and compute something. And so he actually did this. I think it was the 90s, and he demonstrated. There's a cool video of him demonstrating this on like detecting manually handwritten addresses for mail. And he's like putting like handwritten text underneath it, and it's like actually figuring out like, oh, here's the address of this handwritten letter, and like with like an old computer on like I don't know what it was, DOS or some Windows 95 or something.
Oh, is that how the OCR system? Because like now we have ChatGPT. Well, now I'm wondering about whether ChatGPT uses OCR within its orchestration framework. But I remember that OCR became useful with Google probably about maybe 10 years ago, something like that. Were they likely using convolutional neural networks to do that OCR?
Very likely.
Okay.
Yeah, I can't speak for certain, but very, very likely.
Yeah. Okay. Interesting. Um, okay. So we got convolutional networks, and if it's not too proprietary, like what are you guys building? Are you guys training your own LLM, or how are you guys approaching this?
Yeah, so we are certainly not training our own large language model. In general, large language models, um, like they're good for sentences, so they're good for kind of like say something to it. It can kind of say something back, and there's a space for that at Quilter, right? So maybe as we move our UI forward and we want to give the user the option to kind of like converse with their electronics in plain English, cool. We're probably not going to train our own network for that, right? We can grab one off the shelf. Maybe we can fine tune it a bit or prompt it correctly or whatever else, but that's not really what we focus on. So what we have to focus on is a set of algorithms and neural networks that actually put together these boards. And in general, like, we're early enough where we still experiment with a lot of architectures. There's arguments to be made. Like Google actually trained a neural net to do a similar problem inside of a chip design for a TPU, tensor processing unit. And they published a Nature paper about this like a few years ago where they achieved some kind of better than human performance characteristics by using a neural net to do placement of macros instead of a chip rather than having a human do it. And like they used a combination, if I remember, of a convolutional neural net and a graph neural net. Like very cool. Lots of inspiration from that. We've certainly on our side played with transformer architectures and tabular type networks and certainly CNNs and so on and so forth. That's an open question. That's a part of the fun.
Okay. Very interesting. Graph. I love that you brought the graph neural net. We talked a bit about that when we had our call. The GNNs, and one of the things you said, which was really interesting, was that they don't really scale that well. So they're very interesting, but they don't really scale that well. And now you talked about TensorFlow with the convolutional neural networks, and they combined it in order to do that. Um, oh man. Okay, so a lot of good stuff here. What is the AlexNet thing that you mentioned?
Yeah, so this is just kind of a bit of history of machine learning, basically, and it's a pivotal moment that happened. So if you were a computer vision researcher in the 2000s and you were working on some algorithm, like character recognition or like identifying a cat or a dog or finding a human face in a picture, you were not training neural networks, right? The kind of systems that people were using, like one of the popular systems were these things called Haar cascades, where you have a whole bunch of like computational filters that generate a whole bunch of features, and then you do some kind of classic regression analysis to figure out which features, when they're detected, seem to align to a human face. And like that's like the kind of and people genuinely believe that like you would have to basically describe how to detect any kind of thing in an image. So you'd have to like look for something circular, and then that's an eyeball. And if there's two of them and they're so far apart, that makes sense. And look for a rectangle, and that might be a nose, and so on and so on and so forth, right? And what happened with AlexNet was the researchers, I believe it was at Stanford, tried to apply just neural networks to the problem, where instead of hand specifying all of these different features of what to look for in the image, they just allowed the network to see many, many, many images and learn from its own patterns of what works. And the key breakthrough there was that they were able to win this kind of competition called ImageNet, and like within the span of a year or two, all computer vision researchers went from hand-tuned features to all of them training neural networks. And so that was kind of the big kind of original explosion, in my opinion, of neural nets, where all of a sudden, like masses of people started researching this and developing GPU and developing things like precursors to TensorFlow and PyTorch and whatnot. And to now, yeah, like I can scarcely imagine somebody tackling a computer vision problem without a neural net.
Yeah, that's so interesting. What have you learned? What have you learned philosophically from artificial intelligence? What have you learned philosophically about your own intelligence or about human intelligence from knowing as much as you do about this field?
Um, yeah, so I don't tend to I don't tend to extrapolate too much, to be honest. I think the most interesting things that I've learned about just like my own, I suppose my own intelligence or that of others is are maybe about curiosity and hope. Like I can't say that I've learned that like because I know how these things work, that I understand our brain or what the future is or whether they're conscious or not. Like really not much of an opinion there, but like the desire in me for the neural network to have some sort of magic, for it to surprise me. And I think the same thing in people is very, very interesting. Maybe skepticism that people have towards neural networks. Like the debate around
Yeah.
the anthropomorphic level, like view that we have on these things is very interesting.
So
Um,
interesting. But you're saying that the actual magic of, because it does feel like magic, like it does feel like every sort of occult description of what magic is which you do linguistic incantations and then things happen which you couldn't do in other means. And so I love that about it. But you mean like the LLMs surprise you as much as the humans do, or what did you mean there?
well, what I mean, so what I'm referring to in particular is like like the basic math of what's happening inside a neural network is,
Mhm.
at the end of the day, it's not that complicated, right? Like you're basically you're fitting a function, right? Like you have this very, very general function, like a polynomial or like a set of, well, it can't be a set of lines, but something similar. And you have a whole bunch of these variables in these functions, and by choosing them appropriately, you can then build these massively complicated functions. And so, like training a neural network is not that dissimilar from like fitting a line to a bunch of data, right? Like if you did regression analysis in middle school where you had some points that you observed and then you did y equals mx plus b, find m, find b, like that's not horribly dissimilar from the process of training a neural network. It's just a much more complicated function than y equals mx plus b, and you don't have two weights, m and b, you have billions or whatever of them or trillions of
Oh,
them.
interesting. Oh,
So like
yeah. Go for
that
it.
is not like profound in some way where it's like, oh, like clearly consciousness should arrive
Yeah,
out of that or something
yeah,
like that,
yeah,
right?
yeah.
And yet, like when this thing gets big enough, when this function is complex enough with enough parameters, like I see people being emotional when they interact with it. And
Yes.
like that's interesting. Like some people are like threatened, like this thing
Yeah,
might
yeah,
replace me,
yeah,
I
yeah,
hate it.
yeah.
Some people love it, right? Like we hear these examples of like LLMs being friends, or like AI girlfriends are apparently a thing now. Like and but like we want to see something special in there in one way or the other, even though it's just a function with some weights.
Uh, but and we won't go too much more into this lens, but you could say the same thing for human beings. We don't actually know how consciousness works. We don't know really how intelligence works. But if anybody wants to dive into this from a cognitive science perspective, the Awakening from the Meaning Crisis by John Vervaeke, he goes into a lot of this different stuff. But with human beings, we have intelligence, that's clear, but we don't really know how it works. We know we have a lot of the puzzle pieces, but we haven't. It doesn't feel like we've connected them into the whole map of how intelligence works. And people talk about emergence and how an exaptation. So we have a hand. If you look at the monkeys, the hand of the monkey looks similar to ours, but is different, particularly with the opposable thumb. And so that we exapted the hand and created an opposable thumb out of it. And so there could be an argument, and I love listening to arguments like this about the trying to find the secret to intelligence. And a lot of people predicted it is just emergent, like it is just some random evolutionary thing that feels like we're conscious, but maybe have some differences in how it actually done. Do you have any thoughts on that?
Yeah, I mean, this is precisely where my opinions on this kind of stop. Like I admit that I know nothing about how the brain works, and since I know nothing about how it works, it's very difficult for me to make any kind of analogies between how a neural network actually functions and how the brain might function.
Yeah.
And so, honestly, like my thought here is just simply like I hope we do a lot more research to understand the brain. Like I'd love to see the next 100 years of papers that figure this out.
Mm,
But without that, it's I don't venture into guessing.
cool. Okay, so let's go back to electrical engineering. AI. Well, we could talk about business too. What are you most excited about? Not necessarily the hardware that you're building, but about the business landscape that you're entering.
I think for me, both for our company and for this kind of whole industry, the exciting thing for me is like what happens when creating hardware, and in our case, creating electronics, becomes much easier. So I'll make an analogy, right? Let's take something where we can already observe that. So for example, this process of taking a circuit schematic and converting it into a layout, you can think of it by analogy to software. And you can make the analogy that a schematic, this kind of logical human description of what you want to do, is a lot like writing code, like Python or C++ or whatever. Is like a human readable representation of logic. And this process of doing a layout is a lot like compiling your code, just like taking that logic and making it real, right?
Yeah.
And in software, that's easy, right? I write some C++, I click a button, I don't review the ones and zeros that enter the registers of the processor. Like it just happens. And for that reason, as a 10-year-old, I could start making a website or a video game. And I was screwing around with like Flash games when I was a kid. Like awesome. But like, imagine how difficult it would be to make a web browser or Zoom or, an operating system without a compiler. Like if you had to
Mm,
manually go place every single one and zero that was going to occupy gigabytes of RAM and go into a processor and exercise all the different instruction sets that it has. It's like inconceivable that we would have software as we know it today without the compiler, because we take it for granted so much at this point. Now, in hardware, we don't have a compiler. So taking that same extrapolation, what's going to happen when we do?
yeah.
To me, that's in the long term, 10x as many people building electronics, building hardware. It's a lot fewer mistakes. It's far more complex amounts of hardware that we can build. It's faster iteration cycles, and hard to know exactly what it means, right? Same thing, same way that like in the 60s, we probably didn't quite foresee everything the software did. I mean, unless you're Nikola Tesla, but that's the part that excites me, right? A little bit of that, like what will happen once it's 10 times easier, 10 times as many people, and 10 times as many ideas being born.
Yeah, brilliant. The hardware as an analogy for software compilation, different levels of abstraction, basically. Um, now, what's your take? And I know that you may have an interesting insight into this because I did a research into 3D printing, and it led me to basically the one place that I know of that has great business potential for 3D printing was actually in rocketry for developing ceramics and other metals and other things like that related to 3D printing. Are you bullish or are you bearish on 3D printing? Do you guys use 3D printing for your circuit boards? Is there a use for 3D printing?
Yeah, interesting question. So obviously 3D printing has a lot of tremendous use cases, no doubt. I mean, SpaceX is very public about, some of their use cases for, part of the engine and whatnot. They're just quite simply like mechanical geometries you cannot create with the standard, subtractive manufacturing of like milling and whatever else that are possible with 3D printing. I mean, obviously Elon famously talks about like not needing to bring an entire factory with you to Mars, right? Like if you can take a 3D printer, whatever part you're missing, like you can print rather than needing, a crap ton of machinery to make that possible. Now in electronics, 3D printing is, I would say, not really prevalent.
Mm-hmm.
So certainly on the mass manufacturing side, the problem is that the process of creating a circuit board, this process of lithography, scales remarkably well.
Mm.
Like it is very, very cheap and it like can just create, hundreds of millions, billions of PCBs, in throughput in a way that 3D printers just wouldn't be able to do. Now, some exciting things, on the one hand, there are now, I'm aware of at least one kind of commercial at-home printer that can start to print basic circuit boards.
Mm.
And that's really great, right? Because now you're not talking about taking a blueprint and sending it to a manufacturer and waiting for it to be shipped to you for days. You click a button and have that printer like make a
Whoa.
basic circuit board for you on your desk. Not advanced stuff, and it's going to be slow, and you're not going to make a million units like this, but still, for a prototype, remarkable. So I'm very excited about something like that coming to fruition in electronics. The
Okay.
other thing that I'd love to see
Well,
is like
yeah.
three-dimensional geometries in electronics. Like we are so stuck in a planar world due to how lithography works. And I think that from first principles, you could eliminate a lot of like box in a box and stuck to a plane kind of problems if you could 3D print at scale. But I don't currently see a good way to make 100 million units of circuit boards with any kind of printing.
That is so interesting, particularly the first point about the now did you mean the you might have said this, but I might have missed it. The 3D printer can create a semiconductor or can only create the circuit board and then you plug in the semiconductors?
Yeah, just a circuit board.
Just the
So I
circuit board.
think that,
Okay.
yeah, like the notion of a printer making a chip
Doesn't make sense.
is inconceivable to me.
Yeah.
Because we're talking about, I mean, just ridiculous machinery that's, yeah, like if you want to learn about how fabs work, it's fascinating, but like inconceivable to back into a desktop printer to me at this point. But for circuit board, sure, right? Like we were talking about things that are on the scale of, a millimeter, half a
Uh-huh,
millimeter.
uh-huh.
Printers can deposit conductive materials. You can use a non-conductive substrate. So in principle, yeah, you can draw the basic board, and then you still have to kind of buy and hold all of the chips that you're going to
Yeah, yeah,
solder or glue onto
yeah.
it. But like that's a lot more accessible than the status quo with the board itself.
And that's in 2020 I started a foray into prepping, and so I started to think about everything from the nature of prepping, and
Mm,
one of those things was how do I compute after some sort of crazy event,
mm,
and now with this is really interesting because basically what you could do is if you were worried about either like a solar flare or other thing, you could basically put a bunch of chips inside of a Faraday cage and then have a 3D print. Well, I guess you'd have to put the 3D printer in the Faraday cage as well, and then have all the files locally and everything like that. And then you could print computers, or you could just put a computer. I guess you could just stockpile computers. That'd probably be a better way to do that. But really interesting, interesting. Okay. So we got about 10 minutes left. Anything that I didn't ask you that you think is really fascinating about electrical engineering or chip making or circuit boards?
I mean, honestly, I think a lot of it is. I mean, maybe I'm just a nerdy perspective, but the whole thing is fascinating, right? Like the concept that this is even possible, that we can make a little pocket thing that can speak to you and recognize you and drive your car and whatever else is ridiculous. Like when you picture it from the lowest level of like a tiny transistor at the 2-3 nanometer scale to like actually driving a motor and like all of the different levels of abstraction that have to happen, like the fact that we can glue together something so complicated is just amazing. From like individual node to a subcircuit to a macro inside of the chip to the chip itself to gluing together the chiplets and multiple wafers in that chiplet, then the board level and then multiple boards and then connecting that to actuators. And I mean, yeah, if you just really, at least for me, I mean, I don't know how much this shares with the audience, but like if you try to picture each one of those levels, it's like it feels like a house of cards that shouldn't work, but it does. And
It's
I,
so
I think
crazy.
that's fascinating.
It's so crazy. And this is I'm doing a series with my dad where we go back and interview people from the 1980s, 90s, and early 2000s about the rise of the personal computing industry. And it is totally
Mm.
weird. It feels weird. It feels like a strange thing that happened that all of a sudden they took silicon and were able to put intelligence on it. They turned sand into intelligence. And really fascinating. Are you guys like are you remote or are you co-located? What's your take on growing?
Yeah, totally. Actually, before I jump into that,
Sure.
let me ask you a favor for that series. Please interview some folks who were a part of or know about the history of compilers.
History
Like
of
because
colors.
at least for me personally, it'd be very interesting because compilers had the same reaction that automation with AI does today, where people thought oh, like this auto code thing is never going to work. We're always going to have to like write assembly by hand, and it produces garbage outputs. And how can we ever make it precise? To now, it's ubiquitous. And so I personally think there's a lot to learn from how compilers came to be, how they became, private and things you pay for, to then eventually open source, and how they earn trust over time.
We're
I think that there's something to learn for that, for this kind of
yeah,
development of AI applying to solve problems in hardware and maybe just in general.
were
Um,
compilers hardware, or were
no,
they
no, these are
software?
software techniques, right?
Okay,
So
software.
you're
Yeah,
taking in a string of C, or maybe it was Fortran as some of the earliest examples, and converting it into machine instructions, right? Converting it into, hey, processor, go do these very specific things, like
yeah.
a Turing machine almost.
S-
Um,
So Fortran was the first abstraction programming language that could compile.
I want to say I don't think it's the first one. I think
Yeah,
Grace Hopper was historically the first to write a language, and I don't recall what she called her language. But I think Fortran was one of the first, like, kind of like big ones that is still around today that people still use.
great. So do you, before we move on to that next question, do you have anybody come to mind of people that are still alive that no?
That's why I'm curious about
Yeah, yeah.
it. I'm sure
I'll go
there
find it out.
definitely are. There
Uh,
definitely are. I just don't know.
yeah,
Um,
yeah. I'll go
uh,
find it. Yeah.
Yeah. Yeah. Your question about remote. So we currently work completely remote. We have the luxury of working primarily on software. And so that obviously facilitates things. We do build boards for ourselves to validate everything. But boards are pretty easy to have on a desk, to mail. Most equipment you need to work with them fits on a desk. And so that's not a barrier for us. It's not like we're need a factory to create a car. It needs to be co-located. Honestly, I'm pretty bullish on the concept of full remote. I think that there are definitely challenges with it in terms of, the missing water cooler conversation, the missing collisions of brilliance that can happen in office, the missing energy. But like, I think those are temporary. Like, I think fully remote work is a very new concept compared to the tens of thousands of years of co-located work. And like, once we work out some of those things, I think it's going to unlock now the ability to drop all the constraints of we all live in the same place with, wasting time commuting and all these things. So I'm very excited for that in the long term.
Yeah, I think you're right. It's so interesting for me because I up until 4 months ago, no, I have been a nomad, and then now I've finally found my place where I can live for long term. And so up until that point, the only option was remote, not only for my business life, but also for my personal life. And this is actually what part of the reason I started this podcast was that I just have so much fun doing this, and a lot of my friends I've actually either made or interviewed as they're already friends. And so I've lived my life pretty remote, and I just love the fact that soon Starlink is going to be allowed in Argentina, and I can go, get my self-driving car. Apparently, comma.ai. I haven't talked to. I want to interview the founders, but they apparently they've got a thing that you can just plug into a computer, and I'm sorry, plug into a car. And we were talking about the actuator and computer vision model, and basically plug into those things that you were talking about, and then I can get a school bus and install that in the school bus and get my Starlink and go into the Andes mountains and just go work remotely anywhere I want. I'm really excited about that future. And so yeah, remote, it's just like it's like those things you mentioned, those are real. But also, are they absolutely 100% necessary? And if they're not 100% necessary or not able to be replicated, then remote work, like there's no other, it's just gonna happen, right?
Yeah, I mean, I think on the replication factor, like a personal opinion that I have on this is just from my own experience. So I moved here to the States from Ukraine. I was 10 years old, didn't speak the language, moved to Ohio, where I was the only kind of person from abroad and stuck out like a sore thumb. Not necessarily the most popular kid in school at that point. And honestly, like where I found a community and a lot of how I learned English was in
Yep.
video games.
Yep.
Like I played Earth and Beyond and played Eve, these games where people come together and even just in chat forums, like are talking about how do we go raid this other thing? How do we build our empire? Like how do we infiltrate them and sneak a spy in or whatever else? Like, and like I personally felt as much connection to some of the people that I played with as I do with real
Yes.
people in real life. And so like 20 years ago, the concept of a remote, meaningful human relationship where you can brainstorm, be creative, do nice things for each other existed just in this
Yep.
like niche thing of like a video game,
Yep.
right? So like how do we bring that to the masses of work and into an office culture? I don't
Yeah.
know exactly, but like the proof point for me existed decades ago.
It gave me a great idea. It's just like play computer games with your remote workers. Like, but have you tried that?
No, we haven't tried that directly. I think one of the issues is like not everybody's into video
It's
games,
the not
right?
not
Like,
everybody's going to play games. Not everybody wants to play games.
yeah,
Yeah. Yeah.
right,
Yeah.
right. So I think it's like that's not quite it, right? Like I think
Yeah.
that like some of these ideas of like metaverse and whatever else is like maybe we all exist in this video game, but again, like I don't know if that's quite it for everyone, right? Like works for
Yeah.
me, but
Yeah.
like
Yeah.
probably not for many other normal people. So like I don't know exactly how it's gonna work,
Yeah.
but I have some proof points that it's possible.
That's so interesting. Okay. Any roles that you're hiring for that you want people to know about out there in the interwebs?
Yeah, totally. We're hiring a bunch right now. We're hiring for reinforcement learning talent. So anybody from ML and specifically reinforcement learning community. I think one of the exciting things about Quilter is we're one of the few commercial applications of like really interesting reinforcement learning research. Um, we're hiring for an electrical engineer. We're hiring for a DevOps and infrastructure, hiring for a designer. Um, and I'm sure that like by the time this goes live and in 2 or 3 months, like that list will have grown and changed. Come to our careers website. We also always keep open an opportunistic application that if you don't quite fit into one of these buckets, reach out anyway. And let's just talk and see if it makes sense to create a role for you.
Cool. Thank you so much.
Thank you, Stuart. That was a lot of fun.